All right, I'm just going to speed through all of these really quickly. So, how many oxygen atoms are in each formula unit of barium hydroxide? One of these molecules is just a formula unit, so therefore there's going to be 2 oxygen atoms per formula unit. 2. Chemical formulas, molecular compounds are indicated by their prefixes. So di is 2, tetra, or tetr is 4. So just going to input all of these really quickly. Phosphorus is 3 because I've tried. This is nitrogen nitride. And that would be 5. The beginning molecule, if it is 1, it's typically just left without a prefix. However, if it's the second part of a name, that's when it'll have mono. So I really need to include a prefix for that one. Huh? I've added elements that are not, oh, my bad. That is phosphorus. Okay, so molecular solids, they're held together with dipole and dispersion forces, while ionics are held together with their oxidations numbers, or just charges. I guess you can think of it that way. In that instance, molecular solids will have lower boiling points. However, because they are covalently bonded, they won't be easily dissolvable in water and such aqueous solutions. However, because ionic compounds are held together with ionic bonds, that means that when water comes around and its polarity and other things, it can easily separate those ions, and that's where you get like highly conductive solutions. So if we read the first one, substance can't be melted or even softened by ordinary laboratory equipment. That's immediately ionic for me. Clear liquor with a strong smell. If it heated gently, it boils at 115 Celsius. So that's molecular to me. 115 is quite low. It's very slightly above the boiling point of water. Deep red solid with noticeable unpleasant smell. Dissolve slightly in water in a solution of 2 grams in 100 milliliters. So noticeably unpleasant smell. If you can smell something, it means that it's like it can easily become a gas. So I'm going to say molecular for that. There we go. Continuing on. Complete the table by writing symbols. So this is just reference your oxidation table. You can also reference a polyatomic ions chart that you should be given, and on it will be listed the charges of things as well as their names, because their names aren't, there's no noticeable pattern to them. So this one is actually slightly interesting because it's 3 minus and there's a prefix of 4 in the original imperial formula. That means that the anion will totally have a charge of 12 minus. And because there's a subscript of 3 on the manganese, that means that 12 divided by 3 is 4 plus. Empirical formula, so just put them together. If the charges don't balance out correctly, you should be able to just put in a subscript and that should balance things out perfectly. ClO is hypochlorite. Watch out for multiple oxidation state elements here. Those can be tricky. Oh, so this one you can reference your polyatomic ion table, but it's also just easy if you know what these endings are. So basically, because if you notice, they're pretty much the same. It's just that their oxygen number is increasing. So a good just way of thumb is if this is the number of oxygen atoms, the ionic compound with the most oxygen atoms will become per-8. So this basically means it would be like perchlorate or perbromate, etc. And then below that is 8, next is ite, and finally is hypochlorite, like I've written here. It's just a good rule of thumb. Because the polyatomic ion chart is provided, you don't really need to know it, but it's cool. All right, I'm just going to quickly fill in the rest of the table since. Oh yeah, so that Alex warning just now was basically saying, oh, don't capitalize names because they shouldn't be capitalized as they aren't proper nouns. And yeah, that's a thing. I do it because of habit. You shouldn't. I'm not a good example. This is just chemical name to chemical formula. We've covered everything here, so I'm just gonna put a placeholder and move on. In the actual test, this isn't going to be very comprehensive as I assume you already know it as how else would you be able to solve other problems. Ionic versus molecular, you should be looking for non-metals versus with non-metals or non-metals with metals. Non-metals with metals are ionic, as we've already learned. How many valence electrons are in the acetate ion? Reference your periodic table with them. The column number where a element is located is the number of valence electrons. Keep in mind the oxidation state of the total ion. That indicates whether you should be removing or adding electrons to the total number of valence electrons. So here it's 2 carbons, which is 8. 3 hydrogens, which is 3, so 11. Oxygen is 6. 11 plus 12, 23. Add 1 equals 24. Proposed Lewis structure reasonable, you should be mainly looking for octet rule violations, and is the total number of valence electrons correct? So oxygen is 6. So 6 times 2 plus carbon, that is 16. So you should be looking for 8 groups here. As you can see, it obviously violates that. Next is, oh, this is actually ammonia. which is cool. Ammonia is cool. It's a it often ish combines with stuff, and it's the, forgive me, wrong, conjugate base of no, it's conjugate acid of ammonium. So keep in mind, it will pop up a lot, and yeah. So hydrogen 3, nitrogen 5, you should see 4. Yes, this is correct. All of the ones follow the octet rule. Hydrogen is obviously an exception with 2, and nitrogen has a full octet. This is a azide, which is just 3 nitrogens. As you can see, keep in mind this negative here for when considering the number of valence. This should have a total of 16 valence electrons. Here it does. However, it does not have a octet rule, as that right nitrogen is clear violation of that. Let's check. Good. Continuing on, polar or nonpolar, this is just looking at your electronegativity differences. You can look at your just periodic table for this. Fluorine is the most electronegative of all the atoms, as it exists in that perfect space of small but a lot of electrons. Sorry, a lot of protons. So the shape of hydrogen cyanide, this one we can just look at our periodic table again. So hydrogen is on the side, carbon, nitrogen. So I'm just going to fill it out for you. Normally you would guess-ish and check to make sure. But since I already know this structure, I'm just going to write it out to speed things up. Something to consider is just making sure that you're getting all the electrons down. And if you have any lone pairs, they should be going from the central atom if all the other octets are satisfied. So we have 2 electron groups here. The triple bond counts as 1 electron group because they're all close together. And there's just like 2 side atoms. So this means that this will have a geometry of linear, not bent, linear. So this one is a bit long, but basically you just have to confirm, does the geometry match with any of the given ones? So to do this, first you want to check if all the given formulas correctly have 4 atoms. They do. So I'm just going to try and speed through this for you guys. Just trying to do some basic math to double check my stuff. I'm going to give this a check because it does match up. I believe we already saw this one, but I'm just going to do it again because sulfur has this is actually interesting. It has 11, if I'm not wrong. So it's gonna turn out a bit weird. You shouldn't have this on your test, but sulfur has 6 valence electrons. Oh, my bad. I make mistakes sometimes, guys. Give me a break. Oxygen has 6, so it's 24 plus 2 equals 26 equals 13. As you need to do these ones. So that means that this will be 12 plus an S, and that means sulfur is also a check mark. Bromine, 3 oxygens. This will be 7 plus. Yes, this should also be a check. So that means all of these have a similar shape. Sorry, I had to sneeze. Okay, continuing on, I'm going to try and make this video really short. Polar or non-polar? Usually I just like to guesstimate on this because unless I'm actually taking the test, I don't like to spend that much time. So carbon and sulfur, if you just look at the formulas for this, it would be, yeah, it should be non-polar. Oh, I meant annotation. Okay. Sulfur, silicon and fluorine. This one is a little bit more tricky. I would recommend writing this out, like just in general. Don't be like me. But this one, you have to add 4 for silicon, 32 divided by 2, 16. And this is a perfect one. So this one is also going to be non-polar. And hydrogen iodide, just looking at that, I can immediately see it's polar. And the atom closest to the negative side is iodine, as it's so electronegative. It's just going to immediately pull hydrogen. Electrostatic potential map. So that means that you have a very positive middle one and 2 less positive on the sides. So this means that your middle one's going to be pretty electronegative, while the ones on the sides will not be as electronegative. So we can immediately cross out the carbon, oxygen, chlorine one, as that is more than the amount we have up here. We can also cross out this one, as this is iodine, chlorine, and that's only 2. So we're left with the remaining 3. So nitrogen and oxygen too. So first we have to look at their oxidation. So oxygen is more electronegative, and that means that you'd expect it to pull more electrons towards it. And that means that this is probably one. The next one, sulfur, oxygen 2. Oxygen is also more electronegative, which is good. Oxygen, carbon, sulfur. So this one is sketchy because you see this is like perfectly symmetrical, and these are not the same. Like these ones have 2 of these same terminal atoms, but this one's just completely unidentical. So I'm just going to submit these 2 and check. And there we go. Well, give me a moment to get rid of the random stuff on the screen. All right. So is there a hydrogen bonding force? So the main things you should be looking for are your fun atoms. It's just a little acronym to remember which of the very electronegative atoms can inspire hydrogen bonding. So they will become so negative and hydrogen will become so positive because this atom is attracting all the electrons. So if we just look at the formulas, oxygen and hydrogen, I immediately see one of the fun atoms. So this will also be between the molecules of the compound molecules of water, as water also has hydrogen bonding, part of why it's so sticky, if lack of a better word. So carbon, methane, this will be no for both. As between molecules of a compound and molecules of water, this question is really asking, does it have any of the fun atoms? So if I just click continue, so there's so much more to go. Intermolecular forces, hydrogen fluoride, immediately, oh, all of these have dispersion, because dispersion is just an innate property of all bonded matter, because it's just about like, how much mass do you have? Dipole because, and hydrogen bonding, because fluoride is one of the fun atoms, and it's electronegative, it makes it polar. Fluoromethane, immediately, anything with fluorine is just polar. There's no hydrogen bonding in this one because the fluorine's bonded to carbon. Silicon tetrafluoride. This one, as we already saw, I believe, is not polar, so I will not check dipole for this one. this one is also going to be dipole. Oh, and because there's 2 chlorine here, they're still going to bond to the carbon, so it's not going to be hydrogen. Ooh. What kind of intermolecular arc between the xenon atom and the fluorine F2? So keep in mind that xenon is like, it's just trailing this. There's no like forces it can because it's so stable. There's no dipole because it's just a singular atom. And there's no hydrogen because there is no hydrogen. Therefore, it's only dispersion. Next, boiling point. So this one, I would first recommend spying any type of ionic compound as we already defined. You're gonna have the highest. Next is just molecular mass. Carbon monoxide has the lowest molecular mass of all the ones here, and dispersion is one of the most powerful forces. In fact, I would say it's more powerful than hydrogen, just because things with more mass have more attraction. Like hydrogen fluoride, it's not going to stand a chance against like, I don't know, gasoline. So let's see here. They're pretty much identical. The only difference is that this one has hydrogen bonding, and that is gonna make me place it higher than this one. Oh, sorry, that question was about boiling point, if I didn't say it clearly. So let's see. This one is about enthalpy and heat. So heat is basically just like the energy of a substance that goes from warmer to cooler areas. So anything that we see warmer or cooler is just basically about kinetic energy. So temperature is the average kinetic energy of something. And if you think about it that way, anything we feel is hot is just vibrating molecules. And when we burn ourselves, it's just vibrating molecules that are vaporizing our skin cells. I'm happy to offer you that information. So the reason I put time down here, not like heat added, is because this is a heating curve. It's not a curve, but we'll pretend it is. So time is as more heat is added, the temperature increases. This is a fundamental property of matter, and I hope you know it. So each plateau indicates a phase change, because during a phase change, water needs to go into like a liquid needs to go in gas. Gas needs to go in plasma. I don't know why that's an example I'm using. So it needs to go to a liquid. So during that, the temperature actually doesn't change because all that energy is going into breaking the intermolecular forces, like not really breaking, but like separating them, like separating the atoms to the point that the forces between them don't really act. And that means that then they can become their new state, a liquid, gas, etc. So during these plateaus, we can define this like mathematically with the equation Q equals mH. This mH will have a subscript that indicates what state, what phase change is occurring. For example, solidification, liquidification, fusion, liquidification doesn't exist, vaporization, freezing, etc. Meanwhile, you see these slopes, and these slopes indicate a phase of matter. Because during this phase of matter, temperature is increasing until it reaches the melting or boiling point. So during these changes, we can then define this as Q equals mc delta T, or more easily, Q equals mcat. The mcat, yes, I know it's a medical exam that people are very scared. So this is basically saying that this is a mass. This is its specific heat capacity, which is basically the amount of energy to the degree change of 1 gram of something, which if you write it properly, it's just this, or this, yeah. Because there's many ways of expressing something, like you could do amount, mass, and etc. Delta T is just the change in temperature. So something to consider is the value of Q. One should be Q be positive, one should it be negative. Well, when you consider a equation, for example, here I'm just going to do H2O melting. This is not a chemical equation, it's just a physical one, but you should just pay attention nonetheless. So here, it's going from a solid to a liquid. So in a solid, it's actually more stable than being a liquid. So that means that energy will be needed to take a solid form and put it into a more unstable form, if that makes sense. So that means Q must be added to the system. Since Q is being added, addition is positive. Therefore, Q should be positive, and this is referred to as an endothermic reaction because heat is being absorbed by the system. However, in another case, if H2O was a liquid and we wanted to freeze it, in this case, it's going from an unstable to a stable. Therefore, it's becoming more stable, and that means energy should be released because the energy that was keeping it unstable no longer has to be there because it's more stable now. And that means Q is being released from the system. It's being subtracted from the system, and therefore it's negative Q. This is referred to as an exothermic reaction. And that's it, I believe. Covered all the questions, so I'm just going to put placeholder and move on. All right, here are simple unit conversions. So I'm actually just going to do these really quickly for you guys. Remember that the conversion between joules and calories, my lowercase calories, not capital, is like questionable. Sometimes it's 4.186 calories per joule or 4.184 calories per 1 joule. I'll be using 4.184 here. So let me get my handy dandy calculator. Keep in mind sig fix while doing this. Or you can also turn on sensitivity. Nice. Oh, keep in mind this is kilojoules. Make that mistake. Oh, I think before I stated 4.184 calories per joule. Sorry, it's 4.184 joules per calorie. Right, double check. See, woo, correct. Let's continue on. System versus surroundings. I've already covered this, so we will put the placeholder and move on. Okay, the name of the phase when solids can directly become vapor. Simply reference your vocabulary for this. It's condensation and evaporation, freezing and melting, and then it's going to be sublimation and deposition. So the way I remember is deposition is something is being deposited. Gas floats, so solids sink, and therefore if something's being deposited, solids must be forming. So when solids can directly become vapor, process of elimination, it's sublimation. Students are able to label the phase changes. So this one I've already covered as well. Just reference that graph I drew. That is a heating curve. The cooling curve is simply the opposite of that. I don't know why this question is repeated. Let's move on. This just reference your Q equals MCAT and Q equals fusion equations. So if you're given a problem where a phase change happens while a temperature also happens, simply add the Q's together because they're looking at the temperatures of different things, the heats of different things, and the combined heat, the one you should be using is both of them. So this one is negative 40 degrees Celsius. So the conversion between Celsius and Kelvin is plus Celsius 273.15 equals Kelvin. Therefore, we can estimate this to be around 230 over here and 0.6 atmosphere. So simply look at your chart, and that is, I would say, solidly in the liquids. If pressures decrease by 0.5, we can expect it to now lie in the gas, so it will boil. If temperature is decreased by 51, let's see. Yeah, I would say it could go into solid, but the way I look at it, it seems like it's actually going to stay a gas. Liquid. So nothing. Yep, I think that was correct. Yeah, okay. So held at negative 71 and 1.9 atmosphere. This is 201.9. We'll put it around liquid, border to edge that. The pressure is decreased by 0.5. Since it's 1.9, it's going to go down to 1.4, which is still solidly in the liquid. If temperature is decreased by 163 Celsius, dramatic change, I would expect it to go to solid. So it will freeze. Okay. Calculate the energy required to heat 667 grams of mercury from 2.4 Celsius to 12.1, and they give you the specific heat capacity. This one, always watch out for your specific heat capacity units. This one matches up pretty nicely, but sometimes it doesn't. So just plug it into your calculator and solve. Keep in mind that delta T is always final minus initial. Do not do initial minus final. There you go. Even though it says Kelvin here and I just plugged in the Celsius, it doesn't matter, as the change between Celsius and Kelvin is like adding something. So the way I like to think about it is you have a two lines, and when you change the y-intercept of a line, but the slope is still the same, the lines are parallel. So any difference is the same. Here, I don't know if you just noticed, but I did change the sig fix from 3 to 2, and that's because I saw this temperature and I was like, that seems like it's going to be, oh, wait, actually, yeah, actually, yeah. So that's just 2 sig figs, and that's why I just rounded it. Oh, correct unit symbol, my bad. Yeah, so if you look at these, the grams is going to cancel out as well as the difference in temperature, leaving you with joules. Oh yeah, ignore the conventional one, doesn't matter. Chemical change, physical change. The way I like to see this is chemical change. I spelled that wrong. Chemical change. So atoms are actually being rearranged here. Like if you had hydrogen gas and oxygen gas. H2O, combustion, H2O plus CH3. It's gonna make you something like CO2 plus H2O, 2.5 and round up to 5, something like that. But physical change, that means that it's not actually being physically, like the composition is not being changed. And you should be able to get it back without severely doing something to the substance and remaining inside those like physical properties, if that makes sense. So this would be a change of state. You can get the state back by simply putting it in the freeze or something like that. You also can do like, this is like if something was added to water, like salt. Even though it's technically being dissociated into ions, if you ever boil water with salt in it, you will notice that the salt comes back after all the water leaves. And that is proof that only a physical change is coming. Alloys are not chemically bonded together. It's only it's like just because of their delocalized electrons. And so you can actually separate them out. Those are all your physical ones, I believe. But you might have more, so just be careful and consider all things. Calculate the number of hydrogen atoms. This one just use your molar mass. So the way I do this is I just set up a fraction. You will notice I'm using the Alex calculator for this one. It's just because Alex is super picky about like their long decimals. See, like, look, that's like what? 6 significant figures on that molar mass of hydrogen. So it'll mark me wrong if I don't do it properly. So hydrogen atom, so this is the amount, so basically in every gram of a in every mole of a substance, there's a certain amount of grams. However, here we see this is entirely 1 mole, but if you look specifically at hydrogen, there's 16 hydrogens per unit of camphor. That means that if there's 1 mole of camphor, there should be 16 moles of hydrogen. So therefore, I'm going to multiply this number by 16, and that will give me the moles of hydrogen, or just the unit of hydrogen. But it's asking specifically for the number of hydrogen atoms. Using Avogadro's number, you can then calculate the amount of atoms in 1 mole. I'm going to write this out in a second, so you can actually see the dimensional analysis, fancy word for like unit conversions I'm doing here. Let me make sure I did this correctly though, so I'm just going to plug it into Alex and see what they think. So the 24. All right, so I'm going to get my annotator. So you have 140.0 grams of camphor. I'm going to annotate it to cam because I don't have that time. 1 mole of cam is equal to their 6. This is the molar mass, by the way. 6 times 10 plus H times 16 plus oxygen. Now you're going to get the moles of cam. Now, if you have you have the moles, I'm going to say X moles of cam. Now you want to find the amount of hydrogen. Because we see the subscript and there's only just 1 of these, we then can assume this is going to be times 16 H mole per 1 mole cam, if that makes sense. It doesn't have to be mole. You could probably substitute this with like unit or something like that. But it's just a ratio all in all. There's 16 per unit is how you need to think of this. This idea will be elaborated on in future questions. So I'm just going to skip it quickly for time purposes. Balance the chemical equation below. So this one is similar to that concept. You need to be looking and making sure that all your units look correctly balanced. So that means that there should be equal number of the atoms on each side due to the conservation of mass. No atoms are being like removed or added, their organization is being changed. Aqueous iron chloride and hydrogen sulfide gas. So this one you just need to remember how to read it. They'll also give you the formulas for some of these, which is good. And you just need to make sure you copy it down right and always check if it's actually correctly balanced. So if you look here, see that I'll need 2 of these, but everything else looks like it's fine. Just gonna submit, hope for the best. Continuing on, see H bromide. So this one, general rule of thumb for acid space, just look for if there's like a carbonate or hydroxide OH group, and for acids if there's an H. So following that rule, this is a acid base. It's also a double replacement. All acid-base reactions are double replacements. This is a synthesis or combination. This is also another acid-base double replacement. And this is a double replacement, not acid-base, it's sulfate chromate. And it's going to be a precipitation because it's producing a solid. This one, just count your hydrogens and carbons carefully, and you should be good to go. In combustion reactions, water is turned into water vapor because of all the energy. So let's see, 1, 2, 4, 5, 6. 6 here, hydrogen 3, 5, 7, 10, 12. Will be a 6, and therefore I need 18, so this will be 9. Double check. Yeah, aluminum hydroxide. This is basically asking you want to look at your metal activity series and see if it can replace it. And yes, it does look like it can. Oh, but keep in mind that's only so metal activity. There's some metals that can replace hydrogen in acids, while others can only replace it in. Okay, so most metals can replace hydrogen in acids, but only some metals can replace it in water because in water it's already so stable. So aluminum, it's not very reactive metal. It's quite stable actually. So I would say no reaction here. Just look at your metal activity series, and aluminium is usually not even on it. So I think that gives you a reference point to how reactive it is. So here, calcium, this is actually, let me see, it might be an acid base, I'm not too sure, but in general, if this is typically going to be a double, I'm gonna add the prefix of 2, and then there's no carbon here, so I'm just gonna assume it's gonna make a reaction such as this. I'm gonna add prefix of 2 here. See 1 sulfur, there's 3 oxygens. I think this is fairly balanced. Oh, don't forget your shape code. Let's see. You should be also given a solubility chart to double check these things. But a rule of thumb is most things are soluble, so I wouldn't worry too much. Sulfide gas, this is just like an experience thing. It's going to be in a gas state. The way I remember it is sulfide dioxide looks uncannily like carbon dioxide. So yeah, so just read it. Metal sulfides produce the corresponding oxide and sulfur dioxide gas. Yeah, sulfur dioxide there. So MO is a metal. Forgot the name. It's something weird. What is it? Awkward. I don't know my metals. Oh, it's actually I have no idea. Just follow my word and ask and assume it's a metal. If you don't recognize it, it's a metal. Sulfur dioxide. So no prefix on there. That means that since there is a odd number and you need to put 1.5 here, just put everything up to the next one, just double it, and you should be good. Oxides are typically solids. I mean, there's no water in here anyways, so just put solid. Yeah, so just keep in mind the situation. If there's water in the reaction, I would worry about it being aqueous or solid. But since no water is being present, I mean, like, it has to be a solid, right? This one, I believe everyone already knows, but just in case, I'm going to go over it really quickly. A mole is a amount term. It's the same way as we talk about, oh, this is 1 cup of water, or this, I have 1 phone with me. I'm not talking about mass or weight or anything like that. It's just simply an amount. And that 1 mole is the amount of atoms. It's in fact 6.02 to 10 to the power 23 atoms. Whoa, molar mass. This is where mass comes to play. It's basically saying the amount of grams of a substance per 1 mole. Molar volume, this is 1 mole, but how much space does that amount take up in a gaseous form? And that is 22.4 liters. So if I had 1 mole of oxygen gas, I would be holding like, it could fill a balloon that's 22.4 liters big. Molar ratio is like if I had H2O plus methane. Here I have like 1 CO2 and 1 oh wait, this is a horrible example. Let's pretend this is just oxygen. Yeah, and 1 H2O ish. I don't know. Let's pretend this is a balanced equation. And you see per methane, there's 1 CO2. And that means that these should be produced in a 1-to-1 ratio. For example, you could also write this in a recipe form: egg, salt, scrambled. Because this is a ratio, look, if I put in 1 egg, 1 salt, okay, or like 1 mole of eggs, 1 mole of salt, in theory, I should have 1 mole of scrambled eggs because I need precisely eggs and salt in a 1-to-1 ratio to make 1 scrambled. Therefore, if I had 1 CH3, 1 O2, I should be able to make 1 CO2. And that's basically molar ratios. You can use these ratios to compare the amount of CH3 to O2. For example, if I need 1 egg and 2 salts, that means that I need 2 salts for every scramble I make. And that's basically molar ratio. I would say just keep in mind you're dealing with amounts, not masses. And just look at it. You can also think about it in an amount scale. How much will it take up? For example, 1 aluminium is going to take up this much, but if I need like 3 sulfides, it's going to take up way more. So therefore, you would need more sulfides. Okay, molar mass, this one, just use your calculator, shove in your molar masses, and add them up. Find your answer to the decimal place. I will do that to Mr. Alex or Mrs. Okay, measure around decimal. So nice thing is they tell you what units they want it in. So just by knowing that, I'm going to plug it in and solve. So they want 2 sig figs, so I will give them 2 sig figs. I'm going to put mine in scientific notation just to be fancy. see what else. Calcium sulfide. Let's see. Mass of calcium sulfide and participates. Okay, so basically you just take the molar mass and multiply it by your moles, because dimensional analysis says that if you do that, then you have 0.060 moles times number sign grams per mole. These cancel out, you should then have a mass. That's pretty much the theory of all of that. It's also like, as long as you understand what molar mass is, it's the amount of grams per mole. If you have this many moles, you should have that many grams. Add sulfur. Sig figs, there's 2 sig figs, so just 4.3. Sig figs aren't a really big deal on your test since it's going to be multiple choice anyways. So just check the one that looks the most like your answer. Oxygen atoms, right hand side, 3, 1, 4. Stoichiometry, I feel like we already covered dimensional analysis in depth enough. Just gonna skip it. All right, so this is where it becomes tricky. So NH4 whole 3 PO4 is made by doing aqueous phosphoric acid. I'm gonna ignore the state symbols for this one with like an ammonia. I told you ammonia would be important. So basically here, let's first take a look at our balancing. I believe this is the correct balancing. Yeah. So it's 1, 1, 3, 1, 3, 1. So that means you need 3 ammonias for every ammonium phosphate. And you need 1 mole of phosphoric acid per 3 moles of ammonia. So as we said before, it's just like the volumes you need. In order to preserve the mass. Because remember, when we talk about atoms, we aren't talking about their masses. We're just talking about the volume and the amount of them. The amount of atoms on each side of the equation should be equal. And that's the whole basis this molar ratio is based on. Since there needs to be equal amounts of atoms on either side, there should therefore be, they should exist in a ratio that we can compare. All right, so if we have 1.6 moles of phosphoric acid, there's 1 phosphoric acid that goes into this reaction, and there's 1 ammonium phosphate that comes out. Therefore, we expect that if 1.6 moles of HPO4 are reacted, they react with like, who knows what of this? So I'm just gonna say 4.8 moles. Since this is perfectly in amount, you would expect 1.6 moles of ammonium phosphate now. All right. Oh, my bad. Let me bring that back. All right. So H2O plus CO2 combine to form glucose, C6H12O6, and oxygen. So just looking at this, we see that there's 6 carbons. So I'm going to put a little carrot and put 6 there. Then you need 12, so I'll put in a little carrot and put 6 here. So therefore, we have 6, 12, 18 oxygen atoms. So that means we'll have an excess of 12 oxygen atoms, since there's 18 oxygen, right? And then 6 here, minus 6, but you still have 12. Okay, so what mass of water is consumed by the reaction is 7.8 grams of carbon dioxide. This is mainly looking at your understanding of mole ratios. So there's a 6 here, and there's a 6 here. And yeah, those are both 6s. But if you put this as a ratio, 6 H2O per 6 CO2, what does this cancel out to be? H2O per CO2. Therefore, if you put in 7.8 grams of carbon dioxide, that's a mass. So first we need to look at the amount that is. So if you just, let me put my thing up, look over here, 7.8 divided by carbon dioxide. So carbon plus 2 times dioxide. That's this big number. I'm just going to prefix it to 0.177 for the purpose of time. Now, if H2O and carbon must be reacted in equal amounts, what does that mean about the amount of H2O? Well, it means that there's going to be exactly the same amount of moles of H2O. However, this does not mean the same mass. Atoms have different masses, but they're always still one atom. So you can compare it on the volume scale, as I've been saying, but never the mass. So in order to find the amount, the mass of water, mass of water, I need to multiply this amount of moles by the molar mass of water. So therefore, H2O to oxygen plus an O. Now this should equal 3.2 grams. I'm rounding it for sig figs, so it's going to be 3.2. Let's continue. This is a placeholder. This involves gas as a reactant or product. But in order to deal with this one, all you have to remember is when you see a gas and it gives it to you in a volume form such as liters, you need to remember that 1 mole of something is equal to 22.4 liters. So if I had 1 mole of oxygen gas, that means 22.4 liters. But that also means if I have 22.4 liters of oxygen gas, that is therefore 1 mole of oxygen gas. This is simplified. It's like dealing with ideal gases and stuff, but it's just something that you can remember for now. All right, so this question is now dealing with limiting and excess reagents, fancy word for reactants. So if you want to produce ammonia, like everyone wants to, you first have to balance your equations. So yeah, you have 2 nitrogen, the most minimum amount, but that means that you have to have 2 nitrogen here. So the only way to get 2 nitrogen is to multiply the whole thing by 2, and then be like, oh, if I now have 6 hydrogen needed, I can just put 3 here. So there you go. Nitrogen and hydrogen gas, they're in a 1:3 ratio. So if you have 13 moles of N2 and 5 moles of H2, you then expect, oh, well, if I need 3 hydrogen per every nitrogen, that means ideally I need like 39 H2 to react all of this 13. And that means that there's no way I'm going to use all of it. And that means some of it is going to be behind. And that some of it makes it an excess. It's an excess here. And that's why it's called the excess reagent. Right here, if I have 5 H2 and I need to react, well, there's 3 H2 per N2. That means that like this, there's only going to be like 5/3 moles of N2, which is like really small. That means I'm totally going to be able to react all of this. That means that there's nothing going to be behind, and this defines how much ammonia I'm going to be making. So that's why this is called your limiting. It's limiting the amount of ammonia you can make. So if we take this knowledge we've just learned, we pop it into the calculator. Therefore, we just do 5.0. I wrote 5/3, but that's the amount of nitrogen, and an easier way to do it is just take this amount, and since we already know it's the limiting factor, we do 2 moles of ammonia per 3 moles of H2. Put it together, and round your answer to the nearest 0.1. I guess I'll do that. Double check, make sure I'm not. Okay, there we go. Next. Gaseous butane is reacted with gaseous oxygen for CO2 and H2O. This is the same, but it's more complicated because they're giving it to you in grams, and that means you're going to have to convert it yourself into moles. So I'm just going to quickly do that. Also, because my voice is hurting. So what I've done here is I've double checked that oxygen will be the limiting reagent because all of it can be fully reacted. And now I found the molar mass of the carbon dioxide that could be produced by using the molar ratio. And now I simply am going to combine it, multiply it with the molar mass, cancel out the moles, and get the mass of carbon dioxide that could be produced. Keep in mind sig figs. Oh, why are you doing this? Yes, Alex is a bit stupid sometimes, but that's why I don't typically use it. Okay, this is a very similar one, and it's quite literally the same question, but the only thing is they're using the term theoretical yield. That's basically just how much water is going to be given if we calculate it. Because if we do it experimentally, there's always going to be something that's messed up, because we humans have a lot of tendency to err. Like, for example, if you try and pour something out of a glass, all those droplets are left behind, and that's subtracting from the amount you originally put in. And that's for your experimental yield. So if we then take that experimental yield and divide by the theoretical yield, well, now you can see what percentage you got of what you actually got. Okay, I'm going to do the same thing here, and I'm going to be quiet for a little bit. And I encourage you to try and do this problem on your own as well. All right, so I just did that one really quickly, but it's the same exact thing I was doing with the previous one. So this one's a bit longer, but it's the only extra step is you have to calculate the percentage of what you got versus what you should have got. And I'm just going to do that really quickly. So remember, percent error is basically the opposite of percent yield. Percent error is saying the difference between your the one you got and the one you didn't get. For example, if I got 97 on a test out of 100, my percent error is 13. I was 13 off from getting 100. But my percent yield is 97%. I was able to get 97 out of the 100 I should have got. So here, because HCl and NaOH are in equal amounts, when you try and find the limiting factor, a shortcut is to just see which mole is greater, because if they're in the same amount, that means that the limiting reagent is just the smaller one, because that's the maximum amount that can be used up, is if you need one of each. Then if you use up all of one, then what are you going to do with the rest? So we put that together, we get this number for HCl. And when we try and find the NaOH, do some math. You get this number. Now you see this number is larger. So that means that this number is gonna be, oh God, what did I just do? Your limiting reagent. So if you now multiply this by what we know as the molar mass of NaCl, which is Na plus Cl, you get 4.6. So this person was really off. And never be like whoever got that experimental, yeah, because that's really bad. But basically, just find the fraction of what they got. And that's 9.9%. Just really, really bad. So I'm gonna round it for sig figs here. I don't know if it's gonna like that or not. But yeah, there you go. That is all of semester 2 and a tiny bit of semester 1 chemistry. It's 80% because those placeholder questions. Yeah. Good luck. You've got this for finals week. Sure you will do great.